This DVD training program explains the important workmanship standards for evaluating through-hole solder joints. The contents are organized into 4 sections: an introduction, which is common to both Class 2 and 3 training, acceptance criteria, specific to Class 2 and Class 3 products, and visual defect criteria, common to both Class 2 and 3. The focus of this training program is on solder joint evaluation using tin lead solder. While the criteria covered is the same for lead-free, there are important visual considerations between the two types. For a comparison and explanation of these differences, please see IPC DVD 45C, Lead-Free Hand Soldering. This introduction will explain through-hole solder joints, industry specifications for solder joint acceptance standards, classes of products, and solder joint terminology. Let's begin by looking at the parts of a through-hole solder connection. The first part is the through-hole itself. A through-hole is drilled through the printed circuit board during the manufacturing process and is plated first with copper and then tin lead. The tin lead plating is solderable, since it's made from the same materials as the solder itself. This allows for a strong, reliable connection. These plated through-holes are supported holes. This DVD does not address unsupported holes used on single-sided circuit boards. The next part of the through-hole solder joint is the component lead. Components are assembled onto the circuit board manually or by automatic insertion machines. Either way, the leads are formed, usually with a 90-degree bend, and trimmed to the correct length. After the lead is trimmed, it may be clinched or bent over to hold the component in place during the rest of the assembly process. You'll usually see 2 types of clinched leads: partially clinched and fully clinched. There are also straight leads that are not clinched on components such as pin grid arrays, connectors, and headers. The finished length must be long enough so that the end of the lead can still be seen after the joint has been soldered. The last part of the connection is the solder joint. The majority of solder joints are made with eutectic solder. Eutectic means that the solder turns liquid all at once, instead of going through a plastic stage. Through-hole solder joints made from the most common eutectic solder should look smooth with a shiny or satin luster. This means that the solder cooled at the correct rate and was not moved or disturbed during cooling. There are special solders, soldering processes, fluxes, and components that may produce dull, matte, gray, or grainy-looking solder joints that would usually be considered suspect but are normal for these materials or processes. Your company will inform you if these special circumstances apply to any assemblies you'll be evaluating. Through-hole solder joints are almost always soldered from the side of the board where the component lead is trimmed and clinched. We'll be referring to this as the solder source side of the connection. The solder source side is also called the secondary side, or the bottom of the board. The top of the board is where the components sit, and is identified as the solder destination side of the connection. The top of the board is also referred to as the primary side. 2 of the most widely used standards for determining solder joint acceptance are the IPC J Standard 001, Requirements for Soldered Electrical and Electronics Assemblies, which establishes the minimum acceptability requirements. The IPC A610, Acceptability of Electronic Assemblies, illustrates these requirements for many types of solder connections and assembly hardware. IPC has also developed a through-hole solder joint evaluation training and reference guide to provide convenient reference data for solder technicians and inspectors. This DVD explains the solder joint acceptance requirements contained in IPC DRM PTH, so it may be helpful to follow along in your DRM PTH if you have a copy available. Any requirements not covered by the training and reference guide may also be found in the IPC A610 itself. Let's continue now by describing an acceptable solder joint. We'll be specifying minimum and maximum dimensions and other visual attributes for all the various criteria of the solder joint. Sometimes a solder joint will meet the minimum acceptance criteria, although it may exhibit certain cosmetic imperfections that are not detrimental to the reliability of the solder joint. These types of conditions fall into a category called process indicators. The idea here is that the process that created these cosmetic imperfections should be changed, rather than the cosmetic imperfection. This makes a lot of sense because when you fix the process, the incidence of imperfections will be reduced or eliminated. Solder joints that fall outside of these minimum and maximum limits will be considered defects. We'll be discussing what that means in a moment. We'll also be showing the target, or ideal condition for a through-hole solder joint. Notice how the solder feathers smoothly onto the land and up onto the lead. The solder fillet is curved inward or concave. The solder covers all of the land as well as the lead. The texture is smooth and shiny. The outline of the lead is visible beneath the solder. The amount of solder here is just about perfect. Although it's desirable to have nothing but perfect solder joints for every connection on the board, we all know that there are a multitude of factors that can affect the soldering process. For example, environmental conditions of the soldering area or contamination of the solder or component leads can result in a less than perfect solder joint. A solder joint that barely meets the minimum acceptance requirements for a stereo would certainly not be desirable for a life support system. That's why through-hole solder joint requirements are divided into 3 classes, depending on the ultimate use, the life expectancy, and the operating environment of the electronic assembly. Class 1 refers to the general electronic products, which covers consumer electronics such as televisions, stereos, and video games. Class 2 includes computers, telephone systems, and other commercial equipment that falls into the category of dedicated service electronic products. The Class 3 category is for high-performance electronic products. Equipment with high reliability applications such as military, aerospace, and life support systems. Your company may build only one class of products or products within all 3 classes. It's important that you know which criteria to apply. The repercussions of applying Class 1 workmanship standards to Class 3 products are obvious. However, applying Class 3 criteria to Class 1 products make the Class 1 products much more expensive to manufacture. If you have any questions about the type of assemblies you are working with and evaluating, feel free to ask your supervisor or trainer. Now let's return to the subject of solder joints that fall outside the minimum or maximum requirements. It's important to understand that you're not expected to measure every single dimension for every solder joint on the board. But what should you do when you see a solder joint that doesn't meet the minimum size requirements? Do you leave it alone or touch it up? In some cases, especially in Class 3 products, the entire assembly could be rejected for one solder joint that doesn't meet the requirements of the specification. In cases like this, you may have to rework the solder joint. For Class 1 or 2 products, the decision may not be so simple. If there is only one solder joint that is slightly less than the required minimum size, it's important to check with your supervisor or a quality assurance person to determine whether the assembly can be passed or whether it needs to be reworked. This communication will also help ensure that the source of the problem is corrected. On the other hand, when a Class 1 or 2 assembly has a solder joint that is way below the acceptable limits, so much that the joint is clearly too small to hold up during the mechanical stresses of day-to-day operation, you would need to make a decision to rework the solder joint. Again, the decision to rework a specific connection is different for every assembly and every company. The acceptance requirements in the J Standard 001 provide you with information you need to help to make these important decisions. Your company's or customers' requirements may be slightly more or less stringent than the J standard, and of course, those workmanship standards will be the final criteria. But it is helpful to know what the industry standards are, to gain some perspective on the relative importance of each type of deviation. Your job is to know what the current requirements should be for every assembly you build. Our last topic in this introductory section deals with terminology. Regardless of the soldering specification you use, there are standard terms used to describe the attributes of every solder joint. Perhaps the most important term in the entire soldering vocabulary is the concept of wetting. Wetting is defined as the formation of a relatively uniform, smooth, unbroken film of solder, metallurgically bonded to the basis metal. Various degrees of wetting are characterized by the angle of contact between the solder and the basis metal. A smaller contact angle between the two surfaces is a general indication of better wetting and a stronger bond. Larger contact angles can be an indication of reduced strength. On any type of solder joint, the target wetting angle is less than 90 degrees. A contact angle that exceeds 90 degrees usually indicates poor wetting or excessive solder. If a solder joint has a convex appearance as a result of excessive solder, however, it can be difficult to tell whether the surface is properly or poorly wetted. Convex fillets caused by excess solder extending over the land can sometimes be an acceptable condition. Another attribute of a properly wetted joint is the presence of a smooth and uniform layer of solder, both on the surfaces of the lead and on the land. The solder should feather out smoothly onto the fillet or outline of the solder joint and be slightly concave or curved inward. One of the more easily detected conditions is non-wetting. Non-wetting is where the solder simply does not bond to the surface of either the land or the lead. Complete non-wetting is an unacceptable condition for any class of solder joint. De-wetting, by contrast, is characterized by irregularly shaped mounds of solder that are formed when the solder pulls back, almost as if it had changed its mind about wetting. De-wetting is harder to identify and may appear as a partially wetted condition since the surfaces can be wetted at some locations, while the base metal is covered only with a relatively thin film of solder in other places. Various degrees of de-wetting or non-wetting may be acceptable depending on the nature and the class of the final product. Now that you've been introduced to the concept of acceptance requirements, product classes, and soldering terminology, let's examine the acceptance criteria for Class II through-hole solder joints. The following examples will show the minimum and maximum acceptable dimensional and visual requirements for the three perspectives of a through-hole solder joint: the component side, the plated through-hole or barrel, and the solder side. Let's start by looking at the component side. The first parameter we'll examine is land coverage. The target solder connection will have a properly wetted fillet that covers 100% of the land and feathers out to a thin edge over the land area. It is allowable to have 0% land coverage on the component side as long as all other minimum solder coverage requirements are met on the barrel and solder side of the connection. The other parameter for the component side of the solder joint has to do with excess solder. The maximum acceptable condition allows the solder to extend up into the lead bend area as long as it doesn't contact the component body. Here's what it looks like when the solder actually touches the component. Now let's examine the acceptance requirements for the barrel of the solder joint. The first requirement we'll examine is the vertical fill of solder inside the plated through-hole. To evaluate this condition, you must look at the solder joint from both the component and the solder sides. While we've seen that the ideal or target connection has a slightly concave, cone-shaped fillet that rises from the outer edge of the land to the component lead, the solder joints you see every day may not always live up to this ideal. One common variation of the fillet's shape is a slight dip into the through-hole before the fillet rises onto the lead. This condition is especially common on the component side of the board, as gravity can cause the solder to sag slightly into the hole as it solidifies. As long as the solder joint meets all the other requirements for acceptance, some amount of solder depression is allowed. A maximum total of 25% solder depression on either the component or solder side is permitted. This means that a minimum of 3/4 of the